All right, welcome back for another episode of Connie 352. Today we're going to go over the last bit of lecture on the psychometric chart. Going to correct an issue that I had with my slides on the last presentation. We're also going to do a few case studies. So you're going to need a few more of these. So go ahead and print some of these out. I think it'll be a little bit helpful. All right, so the last slide, or rather I should say, the last series of slides, right? We went through this whole thing again, and this and this. I'm not going to reiterate those. I just want you to know that you really need to know how those work. But then I did some examples, and let me explain this particular example. I had a student email me and said, you know, I'm not getting the same values for enthalpy that you're getting. Is there something wrong with, you know, did you enter a wrong value into the application that you use to get this? And let me explain what happened, because yes, I'm very glad that he sent me an email and let me know this, because yeah, those enthalpy values I gave you, they were wrong, but it wasn't wrong because of what he thought. He thought maybe I entered 0.5% instead of 50%. And that's not the case. But let me give you just a little bit of a warning. And I always, if we were in class, we'd all have paper copies of this, and I'd have a paper copy of this, and we do this by hand, and we do it all together. And that's the way I prefer to teach. All right, it is. But I'm trying to do this online. So what I did is I thought, you know, me drawing in pen on one of these and then taking a picture of it doesn't look that great visually. I'm going to go to a computer program and use one of theirs. And that's where this comes from, an online computer program for a psych chart that allows you to put a point in, and then it points all the various outputs. And I made a mistake that I warn a lot of other young engineers against making. And my mistake was I relied on the computer program and I didn't check it and I didn't verify it. Because in a computer program, it's really easy to screw up. All computers let you do is make the same mistakes you're going to make, just faster. What happened, or at least this is what I think happened, on this particular computer program. Remember what I said about this chart only applies at standard temperature and pressure? And if you're at a different pressure, like if you're in an air compressor or a turbine, the whole chart changes, and the thing that's really going to change is those enthalpy values. I think what happened is when I used this program, I wasn't at 1 atmosphere. That's the only thing that I can figure out. And if you look at these enthalpy values that are on here, they are very wrong. So what I did is I actually got a piece of paper out and plotted it, and now I took pictures of it. So the values that I had on there yesterday are wrong. And if you've done this on paper, you realize that, hey, this is way different than the values that I was getting. That's a good thing. That's a good thing to know. In this class and on your final, on your homework, on your exam, and on your final project, please use the paper. Plot it by hand. There is nothing wrong with using a program to verify it. What the programs do is they allow you to get more exact. Like if you plot 72 degrees, 50% relative humidity, it'll give you exactly the enthalpy. And on one of these, it's kind of hard to read it. Let's be honest. It's pretty tricky to read this and get an exact number. I still want you to do it by hand. All right? And I apologize for using a computer program so that it looked nice, instead of doing it by hand myself. So what I've done in the last couple of hours is I've gone through, and here, this one is at 72 degrees, 50% relative humidity. This one was at 95 and 50% relative humidity, and this one was at 30 degrees and 50% relative humidity. I went through and redid those, and I took pictures of them. So if we look at this first one, I did it with a big fat marker, so it's hard to get exact readings, but I used a marker so that you can see it. If I just did this with a pencil or a pen, it'd be really hard to see on the screen, and it'd even be hard to see, you know, in any type of a picture that I took. But I wanted to illustrate it, so I used a marker that can be easily seen. You should do this in pen or pencil so that it's easier for you to get an exact value. So 72 degrees Fahrenheit down here, 50% relative humidity. I circled the 50% relative humidity line. And if you look, and here's a little bit of a tip, use a long ruler. I used like a 1.5 foot long ruler, so I could draw a line from this axis to this axis. And that's the way that you make sure that you get a more exact enthalpy value. They're the same axis. So as you go from 25 to 26 to 26 and a half, you should move that ruler so it's at the same point, and when it crosses that, that will make sure that you get a more exact reading. So when you see my readings on these next 3 slides, you'll see that I draw it all the way across there to make sure that I've got it in the right spot. And at 72 degrees Fahrenheit, 50% relative humidity right there, I get right about 26.6 BTU per pound of dry air of enthalpy. All right. Also, if I take that and draw it out to the right, here's the humidity ratio. And I just rounded, I'm just, you know, so that it's easy to see on these, I just put it's about 59 degrees on 59, yeah. I'm sorry, 59 grains of moisture, and if we take that out, it's 53 degrees for the dew point temperature. All right, now for your homework and then a test, you know, try to get it to at least the nearest half, you know, like 53, you know, 52 and a half, 53, 53 and a half. Try to get it to like the nearest half degree or half grain. I know it's pretty hard, but give it a try. All right, so let's move on. Did the same thing here. At 95 degrees Fahrenheit, 50% relative humidity. Just plot that. Now, I use 50% relative humidity because I wanted to illustrate the differences with the same relative humidity at different dry bulb temperatures. That was the whole purpose of this. For this class, our design outdoor air temperature is 95 and 78. I'm sorry. Well, yeah, 78, but 78 wet bulb. So it'd be just a little bit lower. All right, but I just wanted to show you what it looked like at 50% relative humidity. The enthalpy is around 42.5 BTU per pound. And then if you go out to the right here, it's 125 grains of moisture and a dew point of around 73.5 degrees. 73.5 degrees, important thing here, your whole building is below the dew point of the outside air. All right, and that's the real important thing I wanted to show you there. Okay, and then I did the same thing all the way down at 30 degrees Fahrenheit, 50% relative humidity. The enthalpy is about 9 BTU per pound. Take this all the way out here. It's only 12 grains of moisture and a dew point of 15 degrees. Any condensation, well, obviously will come as frost. All right, and then I did something that I didn't do in yesterday's examples. What I did is I plotted it as if this was an entire psychrometric loop. The term is a psychrometric loop. A loop, something that is going to repeat again and again and again. Remember, the whole point of HVAC system and our calculations is to bring the building into an equilibrium. An equilibrium is achieved when our space temperature stays the same. It's not getting hotter and it's not cooling down. Now, there are forces that cause it to increase in temperature, and forces they'll cause it to decrease in temperature. But if it's at equilibrium, it is going to stay right here. See where I marked RA, return air? That is our desired space conditions, our room air conditions. 72 degrees, 50% relative humidity. The reason we call this a loop is that this air gets returned to the air handler. Once it's at the air handler, we're going to exhaust some of it and make it up with outside air. Here's our next point. Our outside air point, which is at 95 degrees Fahrenheit, dry bulb, 78 degrees Fahrenheit, wet bulb, right here. So we mix that outside air that we're bringing in, ventilation on purpose, we're bringing it in at the air handler. We're exhausting some of the room air. And what happens is as we bring that in and mix it together, that mixed air gets warmer and more moist. We plot that right here. The mixed air has to be on somewhere in between return air and outside air, somewhere on this line. It has to be. Can't be anywhere else. If it was a house and we didn't bring in any outside air, well, down here. If this was a lab space and we were doing 100% outdoor air unit, or maybe for a kitchen, that air would be up here. But for most buildings, offices, schools, those types of normal buildings, we are going to mix some outside air with a bunch of return air. Where this is at, this is that whole percentage I told you. You determine mixed air. All right, mixed air, the dry bulb temperature of the mixed air is the dry bulb temperature of the supply air plus the difference between the outside air and the return air. And you take that difference times your mixed air percentage. In other words, if 10% of the total is outside air, then we are 10% of the way towards there. Common mistake that people make is they ratio the outside air to the return air that's left after you exhaust. Don't do that. The percentage is determined as the outside air over the total CFM of supply air. And that is the sum of the outside air and the return air. Now we make a little bit of a simplification for this class. Remember going back to that diagram that show 100 times in this class where we have the building and the air handler on top, and we have supply air and return air and mixed air, outside air and exhaust air all together in one diagram. For this class, we are going to make a little bit of a simplification, and we are going to assume that the amount of air that we exhaust is the same amount that we bring in for ventilation. On most buildings, the amount of outside air that we bring in should be just slightly greater than the amount that we're exhausting. That gives a building a positive pressure. But for this class, we are making a simplification, and that simplification is that those two airflows are the same. Exhaust air CFM equals outside air CFM. All right. Now, once we figure out where this mixed air point is, plot that, and then it goes through the cooling coil. That's this line. It doesn't really look like a straight line like this, to be honest. First, it will go straight over this way, and then once it hits this dehumidification line, it'll drop down. It'll be saturated coming off the cooling coil, and they'll go across the supply air fan. When it goes across that supply air fan, it'll pick up a few degrees of heat. That's why the supply air dry bulb is just a few degrees warmer than the supply air wet bulb. And for this class, there's a way to calculate exactly, but for this class, I just tell you, yeah, it's about 3 degrees. That's a pretty common difference between wet bulb and dry bulb for the supply air. So 52 wet bulb, 55 dry bulb, and then that air is supplied into the room, and then we start the process over and over and over again. Some key points on here. Notice the difference between supply air and return air. That is our space load. Notice it's mostly sensible, and if you look here, the difference in moisture is very, very low, which makes sense because if we have an office space, most of the heat that's generated within that space is heat coming in through the glass, lights, computers, and the sensible part of people. The only latent part is the latent from people, and it's not all that much compared to the sensible from everything else. So this is the difference between the supply air and the room air, and that is the space load. Once we exhaust some of that room air and make it up with outside air, that air gets more moist and warmer, and then we cool it back down to supply air. That difference is the total coil load. Coil load is different from space load because we add ventilation air to it. And this is the type of calculation I would want to see on your homework and definitely on your final project. All right. Well, with that in mind, I'm assigning homework number 5 today, and it's due in 1 week. And now what I want to do is go through a few case studies. Okay, going back to your handout. Going back to the handout, the first one is a case study for Dick's Sporting Goods. This was in Chicago. Years ago, a former student, an alumni of the program, former student of mine, took this class, called me up. He was now project manager working in Chicago. They were building a Dick's Sporting Goods, and they were trying to open this store by September 1st. It was August, and that particular August in Chicago was hot. I know all Augusts in Chicago are hot, but this one was really hot. It was hot and it was humid. And they were having a terrible time trying to get the building materials to dry out, trying to get paint to dry, glue to stick, glue down, carpets and finish drywall and the whole thing. They were just having an absolute terrible time getting things to dry out just because it was so hot and so humid. So he called me up and he says, "Mr. Perkins, what do we do? We just can't, we can't dry this store out. We can't get stuff to dry. And everything we've done has made things worse." And so I asked him, like, "So what'd you do?" And he said, "Well, we turned on the air conditioners." I'm like, "Really? Okay. How'd that go?" And he says, "Terrible. It just made it worse." I'm like, "Made it worse? What do you mean it made it worse?" "Well, it got colder, but now we got all this humidity just dripping everywhere. It's almost ready to rain inside." He goes, "I just don't understand it. I thought air conditioning removed moisture, right?" I said, "Okay, it does, but there's some caveats to that." Everybody grab your psych chart. All right, grab your psych chart. Go back to the one, right, where you plotted outside air, and just start there. It was hot. It was humid. They turned on the air conditioning. All right. Let's say that the inside conditions of that Dick's Sporting Goods when they went to turn on the air conditioner was 95 degrees, 50% relative humidity. Just remember, we just plotted that. Go ahead and plot it. And so instantly they turn on the air conditioner and they set it to, let's say that they set it to 72 degrees. Okay? Say they set it to 72 degrees. The question that I knew the answer to when I asked him, but I'm like, "Really? What happened?" And he said, "Well, it got cooler, but now it's dripping everywhere." And my question for you, if you're watching this, just take a second and try to see if you can guess. You can pause me if you want. I'm just going to go right into the answer, but pause for a second. And I want you to try to guess what happened. Right? Because this is a simple psychrometric problem. All right. So after you paused and you thought about it, let me tell you the answer. Well, what happened is that they turned on, and if you look at a big box store, and a Dick's Sporting Goods, it's just like a Walmart, just like a Target, just like a Sam's Club, just like all of them. We have one big room and a whole bunch of rooftop air conditioners. And they turned all of them on, and they probably set it to about 75 degrees. Take a look at your Psych chart. What happens when you go from 95 degrees, 50% relative humidity, straight over to 75 degrees? What these rooftop air conditioners did is, remember, the only thing that a rooftop air conditioner can sense is sensible. In other words, there's a thermostat on the wall, and it's reading the sensible air temperature, and when it's satisfied, it just turns off. And that's what happened. All of these air conditioners ran, and they ran for a little bit and then turned off. And why did they only run for a little bit? They only ran for a little bit because they are sized for keeping this store cool when it's all the lights are on, it's full of people, and sun's coming through all the glass on the front. They turned this on at night and let it run, and what happened is all of that load wasn't there. In other words, it cooled it down and then shut off. And so basically, if you just look at 75 degrees, it's straight over. Well, what happens? If you go straight to the left from 95 degrees Fahrenheit, 50% relative humidity, and you stop at 75 degrees, what is your relative humidity? You'll find your relative humidity is about 90%, which is the problem that they ran into. In other words, nothing's drying out. It's cooler. The moisture level may have went down slightly, but the relative humidity, in other words, the air's ability to hold more moisture is practically gone. It's holding almost all that it can, and it's not going to hold anymore. And so I said, okay, what'd you do next? And he says, well, it just kept getting worse. I was like, worse? What'd you do? He goes, well, we just kept lowering the thermostat set points on all these rooftop air handlers, and we just kept lowering the thermostat, and now it's 68 degrees in there, and it's dripping everywhere. Everything is wet. Well, check out your Psych chart. They went all the way over to that saturation line and then just kept going down, but never dehumidified. These rooftop air handlers are capable of removing a whole lot of sensible loads, and they've removed a little latent, but not a whole lot, and definitely not enough to dry things out. So now they got a problem. It's cool and wet now, instead of just being hot and humid. So what's the answer? All right, so what's some possibilities? Well, I gave him a few possibilities, right? I said, well, here's some suggestions. I said, my first suggestion is that, I said, you don't need air conditioning, you need dehumidification. Lowering the space temperature isn't helping you any, and it's actually making it worse. You need to get yourself a job site dehumidifier. Right? Job site dehumidifier. Right? Something like this. And the reason these work, and you can get very, very large versions of these, the reason these work is that it's a refrigeration cycle, but you just sit it in the middle of the room, and all of the heat that this thing, instead of kicking that waste heat outside, which is what an air conditioner does, it rejects that waste heat to the space. In other words, you're removing moisture, but you're not removing any of the sensible load. So it sits there and runs and runs and runs and runs and removes moisture. I said, this would be my suggestion, is go rent a few of these. You can even rent huge ones from like a Contractor Supply or someone like that. One big enough to come in on a truck even, something like that thing. And I said, there, problem solved. And he's like, well, that won't exactly work. And I said, why not? He goes, well, this is the end of the project, and we've kind of used all of our general conditions dollars, and we don't have the money to rent job site dehumidifiers. It's like, huh. Okay. All right. Well, that kind of sucks. All right. So let's go back to our diagram here. And then I said, all right, well, rooftop air conditioners, right? He says, yes. I said, do they have heating coil sections like a gas-fired heater in them? And he says, yes. I said, turn on half of them or 3/4 of them, turn them on air conditioning, and the other half of them, you flip over to heating so that you're blasting hot air in there. Go back to your psych chart. Said what that will do all right, if they were over here somewhere near the saturation line at about 70 degrees and 100% saturated, what that will do is it'll dry out the supply air, but it'll actually add heat to the space and move you this direction. So you'll lower the relative humidity, you'll increase the space temperature, but yet you're still running a refrigeration cycle, which is going to remove humidity. Said, do that. That'll work. Now, normally, I would never suggest running the permanent air conditioning systems during construction. Don't do it. Please, if you can at all avoid it, don't do it. Running the permanent air handlers during construction is just asking for trouble. You're going to pass all sorts of stuff through that air handler that it wasn't meant to see, like drywall dust, paint fumes. You're going to get that stuff in your ductwork. Just my friendly suggestion is don't do it. This particular alumni, they were desperate, and so I said, well, there you go. That'll work. Said run half of these in heating mode, half of them in cooling mode, adjust it as necessary. Maybe you don't have to have half of them in heating mode, but still run it with some heat. He said, well, that won't work either. I said, why not? You told me that they had heat. And he said, well, we're not scheduled to get natural gas to this store until late September, maybe early October. And I said, well, so just call up your utility company and just tell them that you want to move that hookup date, up. See if they'll do that for you. And then he laughed at me. He said, you've never worked with the utility companies in Chicago, have you? And I was like, well, yeah, you're right. I haven't. Apparently, trying to get a utility company in Chicago to do anything early is foolish to even suggest. So I'm like, okay. So that option's out. How about this? I said, do you have any, because this is August, do you have any like portable like job site heaters? Like a direct fired gas something like a salamander or something like that, something like this. So do you have any of those? They're just powered by propane. He's like, yeah. Like, grab them, grab some propane, turn them on inside of your building. Now, word of caution here. Yes, the propane is going to go straight into the room, and you need to, after this is all done, you would need to exhaust this. Probably want to monitor the CO, carbon monoxide levels while you're doing this. But these are propane. I mean, they are meant to be used inside. So I'm like, ventilate a little bit, but turn these on and turn the air conditioners on at the same time. Okay, that should get you a little bit of heat, increase the dry bulb temperature, and allow the air conditioners to run and dehumidify the space. And I want to say that ended up working for them. All right, the problem resulted in this idea that yes, You can run air conditioning to dry things out, but it's more complicated than that. You have to understand, like from this chart, you have to understand all of it. Absolute humidity, relative humidity, dry bulb temperatures, and understand that when you do one thing, it can cause other things to happen. And understand where on the psych chart that you're moving. All right. Ooh, next example. All right, this was a humidity problem in a warehouse. This isn't the exact warehouse, but it looked a whole lot like this. And the humidity problem was that this was for a seed corn storage building in Iowa. I won't say which corn company, but this was a 200, just over 200,000 square foot metal building, metal sides, 25-foot sidewalls, and steel roof, steel bar joist up above. And they were going to store parent corn. And I didn't know this at the time. Parent corn is the corn that other seed corn is grown from. And apparently, it is literally as valuable as gold. Well, almost as valuable as gold. One sack, a 50-pound sack, is worth over $1,000 a sack. And in this building were pallet after pallet after pallet of it. I was thinking to myself, if only there was a market for it, I'd become a corn pirate here and start robbing the place. But I didn't, right? Self-restraint got the better of me. All right. But the problem they were having is that these bar joists were dripping. And that's bad on corn being stored. You want that dry. And this corn, like I said, is very, very valuable. So what to do here, right? Well, they said, we've got this humidity problem. We have no idea. And this is a common issue. All humidity problems result from the same thing. I have something colder than the dew point of the room. That's it. Moist air is coming in contact with something cold, and it's causing condensation. It's simple to understand. It's more difficult to fix. Because the question gets to be is how do we get rid of that moisture? I don't want it condensing. Can I dry things out, or can I just avoid this cold surface? And that's where you really need to start analyzing. It's like, where's the cold surface and where's the moisture coming from? In this particular case, it was dripping at the bar joist because everywhere there was a bar joist was kind of a thin spot in the building insulation, and that was the coldest point. Now, the real question though is, where is this moisture coming from? And here, this is where we get in. So these bar joists were just a little bit colder than the rest of the roof. That's why the condensation was forming at the bar joist. Where it was coming from was the interesting part. All right. The moisture was coming from the concrete. After asking a bunch of questions, I ended up figuring out, okay, where is the humidity coming from? What happened is, this was, like a lot of projects, done in a big hurry. This particular concrete slab was cast, and as soon as possible, they started putting steel up over it and around the sides. Literally within a week of this concrete being poured, they started to enclose it, and shortly after that, it was all enclosed. Now, the problem with that is that as this concrete was curing, it was also releasing moisture. Combine that with the fact that, here, they are wanting to keep this at 50% or 50 degrees Fahrenheit, even in winter. And this should be 25 to 30 degrees Fahrenheit. When it got colder than freezing, it would start dripping. And then it would go away when the outside warmed up again. What was happening is that it was just getting this steel, right? Notice, dew point is 30 degrees, at 50% relative humidity and 50 degrees Fahrenheit, it was just getting this steel cold enough, because there was kind of, like I said, kind of a short circuit there at the insulation. It was just getting it cold enough to drip a little bit. Now, what's the answer? Well, they didn't have any ventilation in this building. It wasn't required. No ventilation, no drier air that's being able to be brought in. The moisture that's in the building is trapped. It's trying to get out. So a little bit of ventilation could have helped. Also, if at those bar joists they would have had a little bit better of an assembly there, they wouldn't have had a short circuit, thermal short circuit right there at those bar joists that caused the bar joist to be a little bit colder than the rest of the building. In all honesty, this particular problem goes away once that concrete dries out. And this is something to be cautious of. Those of you that are general contractors, if you're pouring a slab and you're going to almost instantly enclose that building, just remember that concrete is going to give up moisture while it cures. Be very, very careful that you're not causing some type of condensation while that concrete cures. All right. So this next example, all right, 2 more examples. This next one is unfortunately one that happened to me. We built an addition to our house. We bought double pane Pella windows. And on these double pane Pella windows, right, that first winter, it starts to get cold out, and we start to get condensation on the inside edge of that window. This is a wood frame window, double pane piece of glass. We start to get condensation. And I think to myself, seems kind of odd. And so here's a question. Is condensation on the inside of a window expected or not expected? Right? Pull out the Psych chart and let's take a look. You're going to need to plot a couple points. Condensation started happening, once again, right at the edge, right? Condensation started happening at 30 degrees, when it was 30 degrees outside. The inside conditions were 70 degrees Fahrenheit and 40% relative humidity. Has a dew point, if you look at the Psych chart. Now, plot those points. 70 degrees Fahrenheit, 40% relative humidity. Dew point should be right about 45 degrees. So when it's 30 degrees outside, it's condensing at the inside edge right along the frame. That means there's a problem, and you can prove it using this. So take a couple seconds and analyze it. Kind of think to yourself, well, what could be causing that condensation? Why is that occurring, and how do I know it's a problem? Next, in a day or two after this, it got down to 0 degrees outside. It's still 70 degrees inside, 40% relative humidity. It got down to 0 degrees outside, and frost started to form right there. And then it's obvious there's a problem. And I said, okay, I actually plotted this on a Psych chart like I'm encouraging you to plot it. And by plotting it on the Psych chart, I looked and I noticed, yep, this is a problem and I can prove it. How do we prove it? All right. So think for just a second before you listen to the rest of this. See if you can figure it out. All right. So I knew there was a problem. I could prove it mathematically, but I was in the consulting world. I was really busy. And I asked my wife, I'm like, hey, could you call the sales office that we bought these Pella windows from? Please call them and see if you can get them to respond to this problem. So my wife called. She calls the dealer, talks to someone, whoever the first person that she called, and whoever she talked to, she said, hey, we have a problem with our windows. We'd appreciate it if you'd look at it. There's a problem with condensation. And on the phone to my wife, whomever she was talking to says, ma'am, you don't understand condensation. That's your problem. And she goes, well, you're right. I don't really. But I know this looks like a problem. And my husband says this is a problem, and he wanted me to call you. Whoever she is talking to says to her, ma'am, your husband doesn't understand condensation. And my wife goes, I think he does, but I tell you what, I'll have him call you. So sure enough, I end up calling. And whoever I end up talking to, the nice lady that answered the phone the next day when I called said, sir, you don't understand condensation. I'm like, really? I think I do, because I plotted this on my psych chart, and here's the problem. I said, do you have one handy? We could go through this. And she says, I'm going to let you talk to my manager. All right, awesome. Thank you. Right? So manager gets on the phone, and his first thing is, sir, you don't understand condensation. I said, really? I think I do. And here's why. Do you have a psych chart so we could follow along? He says, a what? And I said, aha, see, a psych chart tells us everything that we need to know. As a student, something I want you to notice before I go through the rest of the discussion with the dealer. Inside air is 70 degrees. All right, the average room temperature, somewhere in here, 70 degrees. Outside average temperature is 30 degrees. If condensation is occurring on this window edge, on the inside edge, that means that the inside edge of that window is 45 degrees Fahrenheit. 45 degrees Fahrenheit is closer to the outside air temperature than it is to the inside air temperature. And the outside air should be separated from the inside of this window by 2 panes of glass. If you think back to our discussion on temperature profiles, it's not possible for there to be 2 different barriers and that little air gap and all that stuff. There is no way that the inside face of that piece of glass can be closer to the outside air temperature than the inside air temperature without there being a problem. Same way at 0 degrees. If it's frosting on the inside face of that window and it's 0 degrees outside, 70 degrees inside, halfway between those is 35. That means that inside face is closer to the outside air temperature than the inside. Frost should not be occurring, condensation should not be occurring, and this is a problem. What was happening is that these gaskets weren't working. Cold air from the outside was getting around those gaskets and cooling this down, and that's how those edges were closer to the outside air temperature, because outside air was blowing directly on them. And as you can imagine, that kind of infiltration is a pretty big problem. So I explained that to the dealer that I talked to, and he said, instead of telling me I didn't understand condensation, this time he said, I'll send somebody out to take some readings. And he did. He sent someone out to take some readings. And then we talked again, and he said, it's too humid in your house. I'm like, 40% relative humidity is too humid? So I don't think so. Once again, I go back to this whole dew point and the frost. No, that's not it. And then he said, well, and my technician tells me that this is occurring in your bathroom, and the mistake you made is putting these windows in a bathroom where there's lots of moisture. I said, oh, well, all right, that is true. It is in a bathroom. However, and we had added on to the house, but as luck has it, we didn't get everything done. We had enclosed the house, but we were still finishing the inside. And that first winter, all of the toilet, the shower, the tub were still in boxes sitting there in the bathroom. No water hooked up to them. And so I said to him, did your technician tell you that the toilet is still in a box next to the window? And he said, oh, no, he did not mention that. I'm like, yeah. So there's not excessive humidity there from the shower because the shower's not working yet. He goes, oh, all right. So then he tells me, and this isn't in here, then he tells me, well, your warranty's void. I said, why is my warranty void? He said, because your warranty's void because you haven't stained the wood on the, you haven't stained the wood jambs and sash and sill. It's like, how does that stop infiltration? It's like, I'm sorry, sir, you need to read the fine print in your in your purchase agreement. Your warranty's void because you haven't stained them. Huh. All right. I thought to myself, wow, two things. One, you just earned a place in my class, right? That's awesome. Forever in my class. And two, years later, right? And you can just search this for yourself. I'm just going to say, just go ahead and Google the Pella class action lawsuit for their ProLine windows. And maybe, just maybe, I had a chance to be an expert witness on one of those, for one of those clients. Maybe. I can either confirm or deny, but it may have happened. Anyway, go ahead and check that out. Moving on to our last example. Metal building with a ventilated attic. All right, we had a metal building business owner. This was a packing plant, not where they were slaughtering animals. This is more like the slaughtering happened somewhere else. They shipped the cuts of meat to this facility, and then in this facility, they just cut them up into smaller and wrapped them in cellophane to get ready to sell. That's what was going on in this facility. It was a ventilated attic. There was roof joists, right? Attic with roof joists and trusses. Wood trusses on the bottom of the wood truss. Right? There was bat insulation between the trusses. There was a sheet of OSB below that bat insulate, or below the truss, nailed to the bottom of the trusses so that the bat insulation sat on that in between the boards. And then below the OSB, they had a sheet of fiberglass, FRP sheet, fiberglass reinforced panel. Right, so back here to this. So open attic, insulation with trusses, below the truss, Orient strand board, and then glued onto the Orient strand board is an FRP, fiberglass reinforced sheet. And I said, all right, so what's going on? And he said, well, we've got a problem. We've got a mold problem in our plant. I'm like, a mold problem? I'm like, that does sound like a problem in a food place. He's like, yeah, we have mold everywhere. There's mold in the USDA inspector's office. We've got this brown gooey stuff dripping from the ceiling. Says, I'm like, okay, well, what did you try? He goes, well, I talked to an architect and they said one thing, and I talked to a builder and they said the other, and neither one worked. I'm like, okay, what'd you try? Well, one of them said, I need to seal up this attic and not let any more air through there. I'm like, okay, did that work? He says, no. And then I talked to someone else and they said to add an exhaust fan through here to blow more ventilation through this attic. I'm like, did that work? And he said, no. They both, when it got really hot out, they both dripped and leaked. And I don't know what's going on. I'm like, okay. So I came and looked. I drove out. It was like an hour drive away. There's access up here. I said, could I stick my head up into the attic and look? And he said, sure. So I got up there, I looked, and then came back down, and I told him the problem. And I'm sure it's an answer rather, that all of you now, with the knowledge of this class, could figure out in literally 5 minutes. So I want you to pause here. Think to yourself, what's the answer? What's going wrong, and how do I fix it? All right, so just think to yourself, well, what could be causing this? All right. Go to this little detail here, right? When they installed this bad insulation, and if you've ever installed like a fiberglass insulation that's got a facing to it, a vapor barrier, you'll read it and it said this side faces in, and you put it in the wall and then you staple it at the joist, and you staple one piece over the next. They'll have a little edge there that comes over the joist so that you'll get kind of a continuous at where it joins. You get like this continuous piece, and if you do a really good job, you'd tape over that as well. Well, they did exactly that. They followed the directions. It says this side faces in, puts it in there, staples it, and then moves on, and then nails the OSB, over there to seal it all up. Well, here's the problem. That works when you have a normal temperature profile. Think about this temperature profile, though. It's 95, 50% relative humidity in the attic, and then below that is just right about freezing. It wasn't so cold that the meat froze hard. They still wanted to be able to cut it easily, but it was right about 32 degrees. And what happens? What's this temperature profile? Where is dew point going to be? Well, if we grab your Psych chart, and if we look at 95 degrees, 50% relative humidity, dew point is at 73.5 degrees. If it's 35 degrees in the area where they're working, 95 up here, 75 is going to happen somewhere in the middle of that insulation. And what will happen is, as the hot, humid air goes through this insulation, because fiberglass insulation is porous, air flows through it easily. It's meant to. We use fiberglass for air filters in a furnace. Air goes through it very easily. So hot, humid air hits the dew point, and then what? Condenses. Has anyone have you ever had to remove from a house or anywhere like batt insulation, fiberglass insulation that has been wet? It's just like a sponge. It's all gooey and nasty, and it's worthless. So once that insulation gets wet, well, even more moisture condenses there. It creates a lot of moisture condensing up here. And what holds that moisture back? The oriented strand board. The oriented strand board absorbs all that moisture for a while, and then at some point the OSB can't hold anymore either. It's completely wet. The fiberglass sheet does hold the moisture back, except that moisture will run along until it finds a joint. And that... It's at this joint that this brown gooey substance is dripping. Where did the brown goo come from? The brown goo comes from the glue in the OSB sheets. So as that gets soaked, that moisture runs and eventually drips from the ceiling. And note, the vapor pressure difference alone is going to force air from higher concentration to lower concentration. All right, so what do you do about this? Right? That was so. I told the guy the problem. I'm like, well, here's your problem. He's like, oh my goodness, what do I do? I said, well, my suggestions. One, you've got to rip out all that bad insulation. Everything that's wet, that's insulation, is worthless. Throw it away. It's disgusting. My other suggestions, that OSB that's totally saturated and all wet, probably worthless as well. You should probably throw it away. You should probably rip down your ceiling. Now, if you dried out those trusses, all right, the building was metal walls, but the roof was wood and wood trusses. Said if you dried those out, those might be okay. But what you need to do is you need a vapor barrier while it's still a vapor. In other words, if we go back to this, your vapor barrier needs to be here, not here. And he said, well, I'd have to shut down production. I'd have to destroy my facility. What you're talking about is very expensive. I said, well, sure, but you asked me what the solution was. You didn't ask me what you could afford. Those are different. Those may be different things. And so I left it with him. And, from there, I told him to find a good builder and go from there, because he had quite a problem. All right. A few thoughts on these case studies. Usually, there are multiple things happening that are causing a moisture problem. But at the end of it all, it's going to be simple. Humid air, something colder than the dew point. That's it. That's the only thing that causes condensation. All right? The trick is finding out where's the cold part and where's the humid air coming from and going to. Right? Never underestimate the amount of moisture that air can carry. It is a massive amount, especially when it's hot and humid outside, like summer. Right? Don't forget that water vapor pressure alone can force vapor through a building structure. And something else, usually, the general contractor is going to be the one that has to handle this problem. They're going to be the ones that get the complaints first. They're going to be the ones that hear about it. As I know, some of you are going to go into the electrical field. Some are going to go into mechanical field. Some are going to go in a highway or whatever. But a lot of you are going to become project managers for buildings. And what I'm saying is, there will be times when you are going to be the ones answering to this. Knowing how to use this Psych chart and thinking about how water, humidity, condensation, dew point temperature, knowing how all that works is critical to figuring out the problem and then coming up with a reasonable solution. All right, I'm going to put homework 5 on the website here shortly, and I'll upload these later today.